Hello, this is the notes for 1.4a and 1.4b. I will make a verbal indication when we're at 1.4b. I'll also put in the description in Google Classroom at what time the 1.4b section of the video starts. So our goal today, I'm not going to write it in, I'll just verbalize it, is to understand basic function definition, notation, and begin applying to some different mathematical situations with functions. So there's going to be two examples that I use to help us understand the four rules and definitions of functions. The first two rules, I'm going to use this time versus temperature example, and then the next two I will also talk about another example that will help illuminate definitions like domain and range. So imagine, let's say we're somewhere on Earth and we're just standing in one spot, and we decide to take the temperature at every hour, 1 p.m., 2 p.m., etc. And we take the temperature at this single spot. We don't move at all. It's going to kind of be important in terms of making sure we understand the rules. And we receive the temperatures accordingly. 1 o'clock it's 100 degrees, 2 o'clock 110, and so on. And then we also have the graph here. Same data. Desert be a prime example of temperature changing, so much within a period of time. We could also connect them. Even though we didn't take the temperature at that time, we could connect them and get a general pattern from that. So the first rule we're going to look at is the relationship of inputs and outputs. So we see at 1 o'clock we have a temperature at 100 degrees. So I ask you the question, is it possible at 1 o'clock for us to take the temperature and to get two temperatures at once, and we're standing in one spot? So is it possible if we're standing in one spot and at 1 o'clock we look at the thermometer and we see two temperatures? No, that's not possible. We only have one temperature. Of course, maybe in some other spot it might be a different temperature, but that would be represented by a different function. So, or predictably a different function. So we're going to call the time that we selected as our inputs and the temperature our outputs. So at each input, we can only have one output. We couldn't have any more. So that's our first rule of a function. I'm going to try typing this. Let's see how this goes. For every input, and there is going to be a caveat to that. There is exactly one output. Now, that's true for every input a part of the domain, which we'll talk more about as we move forward. It's possible that for every infinite input that we could have, that we don't have an output. That just simply means we didn't take the data at that particular input. For our second rule, we're going to look at 1 o'clock and 5 o'clock. If you look, 1 o'clock has an output of 100, and 5 o'clock has an output of 100. 2 o'clock has a different output, so that makes sense that different inputs can have different outputs, but we also see at 1 o'clock and 5 o'clock we have the same temperature. And then we think about that realistically. Is it possible at different times for us to have the same temperature? Absolutely. If I stand right here, there's going to be times where the temperature is, for at least in terms of our observational approximation in terms of the data that we're taking, rounded approximate, that the temperature is exactly the same. So therefore, our second rule is different inputs can have, but don't have to, the same output. But the same input, or one input, cannot have different outputs, as we expressed within rule number 1. So those are our two main rules for a basic function. Functions make up a lot of real-life situations in terms of a relationship of an input and an output, or a relationship of 2 points of data. And we can expand on that in terms of specific type functions, which we'll get into later. But ultimately, those are the two guiding principles of a function. And for equations, whether we're talking about a quadratic or a circle, there are certain equations that can be functions and certain are not. And just because something's a function doesn't mean it doesn't represent a real life situation, but a function's a very important and useful tool in terms of evaluating a good amount of relationships between two sets of data. Okay, so the next two is going to be definitions, 3 and 4, and the first definition we're going to do is domain. And then the second definition that we're going to do is going to be range. So first off, let's talk about domain. Let's go to an example of a person being an input. I'll go ahead and write it down. I am going to erase it at some point, but just so you visually see it. A person being an input, and the output being having an ID, an Illinois ID. And this isn't realistic, but it works to help us understand the definition of domain and range. Let's say everyone living inside Illinois, so say if we got the nice state of Illinois here, beautifully drawn, everyone living inside of Illinois has an Illinois ID, and everyone outside does not have an Illinois ID. So let's imagine if I select, and what we want to do is figure out what people are a part of the domain of this function and which ones are not. So let's say I select someone living in Homewood or Flossmoor. Would they be a person that would have an Illinois ID? The answer is yes. Anyone living in Illinois ID, for simplistic purposes in this problem, has an Illinois ID. So the person living in Homewood, Flossmoor, or Chicago, or Schaumburg, where I live, or Springfield, etc., all of those people would be a part of the domain. But then if we selected some person of all the 7-ish billion people in the world from like Canada or Iowa or Hawaii or wherever, they are not living in Illinois. They do not have an Illinois ID, so they do not have an output. So they are not a part of the domain. So what we find is the definition of domain are inputs that have or produce outputs. Those are the values that are a part of the domain, inputs that produce outputs. And going back up to number 1, for every, where it says for every input, that's for every input a part of the domain. We know that there's exactly one output for every input into a function that is a part of the domain. And then now, very important point. Did we ask anything about the actual information on the Illinois ID? No. We just asked, if we were trying to determine domain, we just asked which inputs have an output or which people have an Illinois ID. We didn't ask anything about the information, and that's an important point in terms of being able to evaluate or determine the domain of a function as we move forward, that we're looking for the inputs that have outputs. We don't want to know anything about the information. And if we think about it in terms of numbers, like if I have an input-output table, we are just, or sets of data, we are just looking for the data that have an output. We don't want to look at what the data is, like if the outputs the driver's license number or the person's gender or birth date, something like that, or in terms of mathematics, what the value is of the output, like the y value of 2, 3, whatever. We just want to know if it has a y value. And then the range is fairly simple. That is simply what our outputs are. That's the actual data. That's saying whatever information on the Illinois driver's license, or excuse me, Illinois ID that we're looking for, like the person's eye color, their birth date, etc. That's the actual data. So this is an excellent framework in terms of understanding the definition of functions and how functions operate from here moving forward. Okay, now next we're going to look at function notation right here. There are two types of notation. that we'll look at in terms of what the function in equation form will look like. But the special notation right here, f of x or f at x is what we say. And what that means is the value of the function at the number x, where f of x is a variable in itself. In fact, it's the output. It's equal to y. So usually, like if we have y equals 2x plus 5, well, sorry, I wrote that poorly. We have f of x equals 2x plus 5, where x, that variable, is our input of the function. And all of f of x, that doesn't mean f times x, that's the output. So whenever we see f of x equals some number, that's telling us in human speak, the output equals this. So typically with functions, this is an example of a function. I think I use the exact same one incidentally. F of x equals 2x plus 5. That's the typical notation we're used to seeing. For those of you in IB, the IB curriculum has this other notation. I'm just emphasizing it to you here just so you get to recognize it as you move forward. It looks like this, f colon x with an arrow into 2x plus 5. And if you look, I have it in words. A way we can verbally speak out this notation is the function f is defined as, and that's this part right here, the function x is defined as x being inputted or being substituted into 2x plus 5. So it's just a nice, neat, different type notation relative to the notation that we're used to with functions. So now we're going to get into the basics of relationship of functions, looking at mapping, set notation, and so on. So if we look right here, in order for a function in a relationship between two sets of data to be a function, it can't violate the first rule. It can have the second rule, but it doesn't have to. The first rule is each input produces one output. So if we look at this, this produces one output. Negative 9 produces one output. Remember, in terms of the function, we don't want to know what these values are. I'm sorry, I'll put that aside. I was thinking about domain. But as long as each input has only one output, then this, the answer would be yes, is a function. In order to violate a function, I would just have to say like 4 goes to 2 of those. If, again, I had a situation like this, where let's say 9, instead of going, let's erase this, let's say 9 doesn't go to here, but 9 goes to here with the 4, and the 4 doesn't go to here. So 9 and 4 both go to 10. That would be fine. That would be the time, 2 times having the same temperature. Over here, this is set notation. So set, these curly brackets is just saying, is the mathematical notation for a set of data. It could be points, it could be names, it could be coordinates. In this case, set A is the data 2, 3, 5, 9. B is negative 6, 0, 6. And we want to see, this is now a set of coordinates. We want to see if A is our input and B is our output. As you see, the A values are in the X position of the coordinate and the B values are in the Y position. So this would be our domain and this would be our range. We want to see if this is a function or not. So what we're doing is looking for the same input twice. And we do have that here, 9 and 9. So we see that 9 produces 2 different outputs. And since 9 produces 2 different outputs, the answer is no. And I'm just verbalized the Y part of that. Now looking at actually plugging into functions. So when we say f of 2, that's saying what would the function's value be at 2. So what we're doing is, my suggestion, especially when we get to more complicated notation, and we will within 1.4b, is that we rewrite the function with open parentheses where our input is, which is typically x, and then we insert what we want to insert into it. And in this case, we are inserting 2 in for x, and then we simplify. F of 2, we keep the f of 2. If we have maybe 4 or 5 lines in terms of simplifying, maybe you just write the equal and you don't write this. I do prefer on the last line that you do write f of 2, but the 4 or 5, however many steps going down, you don't want to write this. You do have to write an equal sign in order for correctness. But that you can not have to write that the way down. 2 squared would give us 4, plus 3 times 2 is 6, plus 5. And writing below it, I ran out of room. That would be, I'm going to actually write it over here. So again, preferably working down. That would be 10 plus 5 is 15. This shouldn't be f of x, it should be f of 2. So what's nice about the function notation is instead of having y equals 15, we have f of 2 equals 15, and then we have both pieces of data within this notation, the input and the output. Okay, so for b, we're going to do the same thing, but we're going to write out the function, x squared plus 3 parenthesis plus 5, and in those parentheses, we have that open that's kind of like a notational crutch I use to help myself make sure I do the mathematics correctly by writing those open parentheses. And in this case, we're plugging in x plus 3. We're not plugging in 2. Note, it's real important to understand that whatever is inside the parentheses here is what gets substituted in for the x values. That will take note as we move again into 1.4b. So I'm going to go ahead and, this time I'm going to demonstrate just using the equal sign, which is okay, going down. This x plus 3 squared, I'm going to expand out. That's x plus 3 times x plus 3. We FOIL or distribute, so x plus 3 times x plus 3. X times x is x. The two middle terms would be 3x plus 3x, which gives us 6x. And then the 3 times 3 would give us 9. And then I have to distribute the 3 in here, so that would be a 3x plus 3 times 2 is 6, plus 5. And I'm going to combine like terms. This will be my last step. So I'm going to write f of x plus 3 equals, I have an x squared, so I'm going to cross that out. I do like crossing that out, but I'm not going to cross it out in terms of making sure that I have this nice and neat at the end. So as I go, I cross out 6x and 3x. I cross those out, and then I have a 9x. And if you see, if you did it, cross out the x squared, 6x, and the 3x, you just have 9, the 6, and the 5, which then add together to give us, 20? I think I did something wrong there. Maybe not. No, I'm just from 4. I think that's the right answer in terms of the calculations. Just remember from last year, the last time I did it, those are different numbers, but it's looking okay. All right. So example 4, this is what's called a piecewise function, where the function's broken up in two different pieces. So this part up here is saying determine our outputs when x is less than or equal to 1 by using this part. When x is greater than 1, we're going to use this part. So let's go back to the time temperature example. Let's say we found a pattern within the data and create an algebraic equation to represent the change in temperature. Well, maybe we defined in the times less than or equal to 1, like maybe in the past, versus like 0 would be the time that we started, but let's say we had data before 0 for some odd reason, or someone before us took data. And then we started taking data at a time of 0, but we had the data prior to 0. We would have data in the negative region, and with that time temperature example. And I'm sure we could come up with many more examples where negative inputs would be applicable. So what this is saying is we would determine the temperature at a particular time less than or equal to 1, time less than or equal to 1, we'd plug it into here. If it's greater than 1, we substitute it in for here. So over here, A, B, and C, they want to know what the temperature is at a time of -1, at 1 and 2. So at f of -1, since f of -1, or -1 is less than or equal to 1, we're going to substitute it into this part. And that will simplify. I'm just going to do it over here. This isn't preferable notation, but I don't want to run out of room. That would be -1 squared would be 1, plus 2 would be 3. Now we're going to substitute in f of 1, and we look at our piecewise function. X is equal to 1 up here at this top part of the function. So since we're looking at the value of 1, that would satisfy this part of the piecewise, which means we plug in 1 to the top part. So we have 1 squared plus 2, and then we simplify. 1 squared is 1, plus 2 is 3 as well. And then we have our last part, f of 2. And coming back over to here, since in this case x is greater than 1, 2 is greater than 1, that means the function is defined at 2 by this part. To determine, let's say the time is 2, to find the temperature at a time of 2, we're going to substitute in for here. So I have 2 times blank squared plus 2. So I'll make sure that's right. Yes. So now I'm plugging in 2 in for the x. And now I simplify. 2 squared right here. 2 squared is 4. 4 times 2 is 8. 8 plus 2 is 10. All right, moving on to example 5. It says for all real values of x such that f of x equals 0 for f of x. So if we look at this notation, remember x is our input and f of x is our output. So in this case, we have f of x, our output, is equal to 0. Think in the time temperature. This is saying we know the temperature is 0. What are the times of x when our temperature is 0? So when we come over the function, this is important to understand that f of x is an output, is a variable in itself, and we're substituting 0 for all of it. So what will that, and then we find x's, which tell us the times that our temperature is 0. So we're going to substitute in 0 for f of x, and we have x cubed minus x. And after we plug in 0 for f of x, note, look at here, instead of f of x, we have 0. Now we just solve this for x. Well, set equal to 0, we factor out an x, and we get x squared minus 1. And now we set both parts equal to 0. As we know, if we have two terms set equal multiply and set equal to 0, one of them has to equal 0. We'll talk more about that. Don't want to take up too much time in the video to explain zero product property rule. Just clean this up a bit. So we have 0 equal to x. There's one of the answers, and the other, we could factor that x squared minus 1 more, or we could simply set that equal to 0 and solve. That would have been difference of 2 squares. If I add over the 1 in square root, that would give us x equals plus or minus 1. So ultimately, the 3 times that the temperature, if this is what the function is representing, the 3 times in which the temperature is 0 is at the time of 0 and positive and negative 1. Moving down to example 6, we want to find the inputs x for when f of x is equal to g of x. So imagine if we have 2 people standing in like different parts of the world and they're taking the temperature, and person f, whoever that is, they have a function like this that represents the temperature at a particular time x, and then someone else is standing somewhere else and they take the temperature and their function is this, and we want to find at what time was their temperatures the same. So f of x equal to g of x, we can think of this being substituted in for f of x and this being substituted in for g of x. Or we can think of it as simply the outputs being set equal to each other. And then we want to find the time x by solving. Since we have non-like terms, but we have common variables, moving it all to one side. If we subtract this to the other side, I'm not going to write over there in the interest of space, would give us negative 4x squared equals 0, negative 2x squared minus 2x squared. And now we factor out an x squared minus 4, and then once again we're going to go ahead and solve by setting both equal to 0. X squared equals 0, x squared minus 4 equals 0, square root over here, we get x equals 0, and over here, move over the 4, square root, we get plus or minus 2. So these 2 people took their temperatures, and they have a function that represents the change or how the temperature exists over time based on the data they collected. And we found out that comparing the 2 functions, that their temperatures were the same at time of 0 and a time of positive and negative 2. Okay, this example 7, I believe, is the end of 1.4a, and then we'll move on to 1.4b, which is the difference quotient. Determine the domain of the function. So domain is inputs that have outputs. So depending on the problem, we're going to approach this from a different angle. And what I offer to you is that most mathematical functions, for instance, like quickly, if we do a graph here, like a cubic, if we look at that domain, we're asking what inputs have outputs. Well, if we drew a vertical line for each x value, like there's an x value of like negative 2, negative 1, etc., it's going to cross the graph, which means that all these inputs have outputs and all the x values are a part of the domain. Again, it doesn't matter what the output is, just that this x value has an output. This vertical line crosses at that point, and therefore it has an output. And we'll talk about the vertical line test later, as that may have come up in your mind. So this, what I suggest to you, even if we have a broken up graph, like a piecewise, looks something like this. Most functions, they have more inputs a part of the domain than not. They have most of the graph typically in real life situations have more inputs than outputs. So what I offer is that instead of looking for our inputs that are a part of the domain, we're going to look for the restrictions, because there's predictably going to be less restrictions on the domain, or less inputs that are not a part of the domain versus inputs that are a part of the domain. So when I look here at the first problem, this is just note I'm using that IB notation. It's the same as f of x equals x squared minus 4x plus 5, just a quadratic. We're going to ask, okay, what restrictions do we have on a quadratic? Well, when I look at this, I go, okay, well, there's no like square root like I have in B, or I'm not dividing by something. We know with the square root, can't square root negative numbers to get real numbers, and we can't divide by 0, so it's maybe a little more obvious on these two what our restrictions are, and we will get to those. But if we look at this one, I go, I don't know, there's not like obvious restrictions, so I'm just going to try looking at negative numbers first, all the negative numbers, then 0, and then the positive. So if I plug negative numbers in for here, we just have to ask ourselves. We don't have to calculate. We just have to ask if it's possible. If I plug negative numbers in for here, any negative numbers, will I be able to square it, multiply by -4, and combine all like terms? Of course we can. You can square negative numbers, you can multiply them by -4, and you can simplify. So all negative numbers are going to give us outputs. If we do 0, if I plug 0 in, that will give us an output again as well. In that case, 5, because these terms cancel. Again, we don't have to know what the output is, just that it gives us one. And then we also look at positive numbers. Positive numbers also can be calculated, and therefore give us outputs. So here we have no restrictions on the domain. So the way we write that is domain by putting a D and then colon. And then we're going to use interval notation, which, if you recall, looks like coordinates. And that all real numbers in interval notation go from -infinity to positive. Remember, that's an interval which stretches from the -infinity value, which is just a concept, it's not really a value, but -infinity, the first one, -infinity to the second one, positive infinity. So this is domain interval, this is interval notation for indicating that the domain is all real numbers. Here, on the second one, we are going to look at what's our restrictions on the second one in terms of real numbers. Well, we know the radicand, which is the value underneath the radical, has to be positive, or 0 or positive, in order to square root it to produce a real number. If it's negative, that produces an imaginary number, and we're not dealing with imaginary numbers in terms of a function on the real coordinate system. We're dealing with positive or real numbers. So this has to be greater than or equal to 0, because you can square root 0 and produce a real number. It's 0, and positive numbers. So this is how we're looking for the restrictions, and the restrictions are numbers that aren't 0, and therefore the non-restrictions are the numbers that are greater than or equal to 0. And now I solve for x, I add over 5, so x, the domain for this will be x greater than or equal to 5. We are going to write that in domain notation. Our first value is 5 and then goes greater. I'm going to use a bracket, which means it includes the value 5 and then goes off to infinity, 5 to infinity, and we use a parentheses. Parentheses means it doesn't include that value. For infinity, we always use parentheses because infinity is a concept, not a specific value. Now we look at C. C, our restrictions on a fraction is that the denominator cannot equal 0. So that's what I do. X plus 5 is not equal to 0. And then I'm going to subtract over the 5. So x cannot equal -5. So if we think about this on a number line, we start out at -infinity. And then we go to -5. It cannot be -5. And therefore we have parentheses, union, which stands for or, meaning the domain values are going to be on that interval or this one, which is going to start at -5 with an open parentheses and then goes off to infinity. Now, we start the 4-point our 1.4 notes, 1.4b notes. And the 1.4b notes is going to be working on simplifying what's called the difference quotient. Now, the difference quotient is not just, this is an example of the difference quotient right there, f of 5 plus h minus f of 5 all over h. This is an extremely important expression. In fact, it's the fundamental math skills necessary in order to get the foundations of calculus. And what calculus does for us is it evaluates instantaneous rates of change. So let's imagine if I'm driving 100 miles and it takes me 2 hours. Well, that would be an average of 50 miles per hour. But at a time of like 1.5 hours, how fast was I going instantaneously at that? It's like thinking about as you're driving and someone goes, how fast are you going? And you look down at your speedometer and say, oh, I'm going 72 miles an hour right now. That's not an average rate of change. That's an instantaneous rate of change. And that's what calculus does for us. As we know, our universe is dynamic, and if we can't evaluate instantaneous rates of change, then we cannot properly represent our universe and the behavior of the universe and come to a better understanding of it, and therefore use it for ourselves as humans. So that's why we, at this point, are just working on the difference quotient. Now, the difference quotient, though it may look daunting, as I know you've seen this in the past, this expression and the mathematics involves two things: substituting values in for some variable, and then simplifying properly. So the first step, if we want to substitute them properly for this, we need to know what f of 5 plus h is, and we need to know what f of 5 is. And whatever those are, we are then going to write out this expression and substitute those in. Now remember, our input is what's inside the parenthesis, and the output is what's outside. So if I want f of 5, that means we're going to take 5, plug it in for f, and simplify in some capacity. If I want f of 5 plus h, we're going to plug f of 5 plus h into x, and then simplify accordingly. So before we do the difference quotient, I am going to write out what f of 5 plus h is, f of 5, and then once we have those, we are then going to substitute in for here. So the first thing we're going to do is figure out what f of 5 plus h looks like. And then we're also going to find what f of 5 looks like. Now, let's start out with the f of 5, just to recall that what we're doing is just writing out the function, and this is where it's going to be helpful to use that mechanical crutch of just writing in open parentheses wherever there's an x. And in this case, the x that we're substituting in is 5. Now, we could simplify that, but we're just going to leave it right there for now. Up here, we're going to do the same thing. 5x plus x squared. And note I gave myself a little more room because now this 5 plus h is going in for there rather than just a 5. So I'm going to do this in a different color to indicate that 5 plus h is being substituted in for x, just like 5 was being substituted in for x. Right, so now that we have that, we can now write out the difference quotient. This right here. But instead of f of 5 plus h, I am going to write an open parenthesis. Minus, instead of f of 5, I am going to write an open parenthesis, and it's all over h. So let me explain again. What we are doing is substituting in for the output f of 5 plus h minus the output f of 5 all over h. F of 5 plus h minus f of 5 all over h. Now, what does f of 5 plus h equal? It equals this right here. So this is a variable, and we're substituting all of this in for that variable. So I have 5 plus h plus 5 plus h squared. I took this and substituted it in right there. Now I'm going to do the same with f of 5. F of 5 equals this. Since this variable equals this, I am going to substitute it in right there. 5 times 5 plus 5 squared. Again, this goes in right here, which looks like that. This is now the setup for simplifying the difference quotient. So now I'm simply going to do the simplification. What can I do in here? I can distribute the 5 in. Here I am going to FOIL. And over here I am going to simplify the numbers. So let's see what that looks like. Here's my large division bar. And I have 5 times 5 plus h. I'm still going to keep the parentheses here. You don't need to. 25 plus 5h. That was this part right here. And now I have to do 5 plus h squared plus 5 plus h squared would be 25 plus 10h plus h squared, foiling out, minus f of 5, which would be right here. Whoops. Right here, 5 times 5 is 25, plus 5 squared is 25, so 25 plus 25 would be 50. Note, you may have thought, Mr. Fossey, why can't I simplify that up here at the beginning? Because we may have a general one. It may be, instead of f of 5 plus h, it may be f of x plus h minus f of x. So I wanted to indicate that if it's generalized, you may not be able to simplify it right off the bat. You can if you want, though, if it's specific like this. And now we can continue. Let's see, we simplify from here. I'm going to work down. So let's look at our like terms. I have 25 plus 25 is 50. Minus 50 gives us 0, so that crosses off. And now I have a 5h and a 10h, which gives us 15h. So I'm going to write that out, 15h. And then I have an h squared all over h. Now, if you did this correct, all of these terms will have an h in them. That doesn't mean it's correct if all of them have an h in them, but that's a semi-check to see if you did it correct. You should not have any constants left over here. Now, if I want to simplify, I can factor out an h, which leaves us with 15 in the numerator, which leaves us with 15 plus h times 15 plus h, and I have an h in the denominator. That cancels, and that gives us our final answer of 15 plus h. At this point, this is just practicing a skill. We don't know what the meaning of this is yet, but it has significant meaning once we get into calculus. All right, so let's look at this one. This one, the difference quotient, is h of x minus h of 4 all over, there's no function there, it's just x minus 4. So we know what h of x is, that's this right here, but we don't know what h of 4 is. So we don't have to write out h of x because we already have it, but let's write out, before we do the difference quotient, let's write out what h of 4 looks like. H of 4 would be plugging 4 into this function, which is 1 over x, and we're plugging 4 in. So that's our h of 4. Now we're going to come down and do the difference quotient, parenthesis, h of x is going here, minus h of 4 all over x minus 4. H of x, once again, h of x equals 1 over x, so h of x is right here. So what does h of x equal again? 1 over x, so that goes right there. And then h of 4 equals 1 over 4, so that's going to go right here. And this is an example that we have again of complex fractions. We have two smaller fractions. These are fractions as well. In fact, I'm going to write those as x over 1 and 4 over 1. And this is that example of multiplying by the LCD of the smaller fractions in order to simplify the larger fraction. We're going to multiply that by top and bottom of the larger fraction. So if we look at 1, 2, 3, 4, our LCD would be times x and also times 4. These are 1, so that doesn't add anything to the LCD. So we are going to multiply top and bottom of this large fraction by 4x over 4x. Now remember, this aligns with the numerators because this is over 1 within the numerator of the larger fraction. So this aligns with the numerators of those smaller fractions. So if I do that operation, I go 4x distributed into here, I'll have 4x over x, and the x's cancel, and we'll be left with 4. If we distribute this into here, we'll have 4x over 4. The 4's cancel, and we have an x left. And note we have a minus sign between them. On the bottom, as we distribute in, note this is in parentheses, this is in parentheses. If we think of it over 1, this is distributing into the numerator. Nothing's going to cancel. Now, when we do this, it ultimately helps without distributing in. Just write it as is because we may have some nice, neat canceling. And that's typically the preferred mechanics or procedure when you don't have any terms or fractions canceling. Just distribute it in, but don't multiply them. Just write it out. 4x times the quantity x minus 4. So if we look at this, is there any simplifying we can do? Well, if we look at this, this and this look very similar to each other. So watch this down here below. If I have 4 minus x, I reverse it and put the x term first. That'd be negative x plus 4. I can then factor out a negative, and that gives us the opposite of negative x minus 4. So that's nice because now this is the opposite of that, and we can have terms canceling. So that's what we're going to do. We are going to take the numerator and flip them, factor out the negative. In the denominator, we have 4x times x minus 4. And now we're in terms of multiplication, so those cancel, which means we have negative 1 left in the numerator and 4x in the denominator. Again, this doesn't make total sense why we do this, but it will as we move forward into calculus.